Okay, acids and bases. This is really the beginning of the end. To be honest, we have acids, bases. This is our last big unit. After that, we have one test and then the exam. So we have the acid bases test. We have a test on the last of the equilibrium, which is solubility, and then electrochemistry, which is actually really easy. And then that's it. Then we take the exam. So we'll be reviewing after these next two tests. We got two more to go. Okay, so acids and bases. So we're going to do just a preliminary talk about acids, bases today. Tomorrow we'll do pH. That's really the big one. All right, so there's a few ways that acids and bases can be defined. An acid, and this is the big one for the AP test. The AP exam loves this definition. They will mention this one to a small extent. But the big one is the first one. So the Bronsted-Lowry definition of an acid is a proton donor. Now, a proton is really a hydrogen ion. If we think of hydrogen in terms of protons and electrons, protons, hydrogen has one. That's what makes it hydrogen. One proton in the nucleus. And if it's neutral, it must have one electron. Otherwise, it would have a charge. So one proton and one electron. And the most common isotope of hydrogen has 0 neutrons. So hydrogen with a mass number of 1. If we change it into hydrogen plus, so hydrogen with a +1 charge, now the proton stays the same. So you still have that proton in the nucleus. So if we say we had +1 in the nucleus and then we had 1 electron in the first energy level. If we made it a +1, that means it doesn't have any electrons. We took the electron away. And its most common isotope, again, has no neutrons in the nucleus. So if we go back over to our atom here and we remove this 1 electron, all you're left with is a bare nucleus. And so the way they refer to that is they call it a proton because it's a proton in a nucleus. So hydrogen ion and proton, same thing. So we say acids have the ability to donate or give away a hydrogen ion. A base then in this particular definition is something that can accept that proton or accept the hydrogen ion. Now a more generic definition, which we're going to use, like I said, a little bit is talked about, more so with the math problems with this, not so much talked about. But an acid is a substance that when dissolved in water will produce something called the hydronium ion. Now really it's just a hydrogen ion again. So it's an H+, a proton. But what they're saying is it's so reactive because it's a proton when you dissolve it in water. So we're putting acids in water. So there's lots of water molecules around. That hydrogen ion attaches itself to that water molecule. And instead of H2O, you have H3O with a +1 charge. And that's called the hydronium ion. We are going to use these two interchangeably as the AP test does. I prefer this one. You'll see why when we start doing the equations. I think it's a lot easier to understand the chemical equations with H3O+, but then the AP test likes H+. So I will always make sure to say that, those two things are considered completely synonymous. An H+ or an H3O+ is really in water. So again, no both. All right, so something that is amphoteric has the ability to act as both an acid and a base. So it has the ability not only to donate a hydrogen ion, but also to accept a hydrogen ion. And this term right here, I've never heard referred to in regular chemistry. They do talk about that in organic chemistry, labile. All it means is mobile. So a mobile or labile is a labile proton. So the ability of this proton to move, the hydrogen ion to move. Okay, so the first part of this then is following the dancing hydrogen ion. Conjugate acid-base pairs are related by a hydrogen ion on either side of the equation. Now that's not a very good definition. I didn't write that, and I wish I read it before I just put it there because it's terrible. But here we go. So this conjugate, really it's just another acid base on the other side of the equation. So we say we have an acid and a base on one side, and then we have an acid and a base on the other side. The acid and the base on the other side are referred to as conjugates because they're formed from something else. Remember conjugating verbs? So they're formed from. So the base forms a conjugate acid. It really just, the base becomes an acid. And then the acid on the other side of the equation becomes this conjugate base. But again, just acid base. So you have an acid base on the left-hand side, you have an acid base on the right-hand side, but then you also have acid base pairs going from the left to the right. So the acid on the left becomes a base on the right, the base on the left becomes an acid on the right. And then going back the other direction, it works as well. Look at this first example. So find the dancing hydrogen. So look on the left-hand side and see what does it match up with on the other side? Where is its pair on the product side? So you have NH3, can't become OH. So NH3 becomes NH4 plus, which means it gained an H plus. So that makes that the base. Now the base, remember, as I said, becomes the acid on the other side. That is sometimes referred to as the conjugate acid because it's, again, formed from the base. But you could, again, just call it an acid, acid-base pair. So there's one acid-base pair. The other one then must be water and H or OH minus. So that makes this the acid. Well, why is it the acid? Well, if we think of water as HOH, or better yet, H plus and OH minus, so then you can see what happens. So there's where the hydrogen came from. So this one is donating a hydrogen or losing. So that makes that the acid, and then this accepted the hydrogen. And so that makes it the base. So gaining a hydrogen makes you a base and you become an acid. Losing a hydrogen makes you an acid and you become a base. Now look at it in the other direction. If we start here with the NH4 plus as an acid, going in the other direction, it loses a hydrogen and becomes NH3. So here it's acting as an acid, losing the hydrogen to the OH and becomes the base NH3. So you can see it does work in both directions. Let's look at this one. So once again, following the dancing hydrogen. Well, I chose this one because in this one, water is acting as an acid. And this one, it's going to act as a base. How do I know? Well, it's going from H2O to H3O plus. So it added a hydrogen. It gained. Where did it gain it from? Well, that lost. And becomes the base. So the acid becomes the base becomes the acid. So in this case, water is acting as a base. So there's that amphoteric behavior I mentioned up here. Amphoteric, the ability to act as an acid or a base. So water is a big one. It can act as an acid in the first one. Excuse me. And it can gain a hydrogen. It can act as an acid in the first one and lose a hydrogen, or it can act as a base in the second one and gain a hydrogen. So hit pause and try some of these. I'm going to make my way down the answers. So hit pause and see how it goes. Or even watch the first couple, then hit pause and see how it goes. All right, so label the following acid-base pairs. So follow the dancing, H plus. That's really what we're looking for. So comparing the left to the right, and the ones that we know are acids are actually really easy to pick out. And I do want to point out ammonia as a base. So one of the things we learned about ammonia was that it acts as a weak base when we classified it in terms of net ionic equations. Well, there it is acting as a base. So there's the definition. That's why it's kind of hard to get all of that in first year chemistry. All right, so NH3 is becoming NH4 again. So this is the base. There's the acid. That makes this the acid. Yep, and that became the conjugate base or the base. Acid, base. So this must be the base and then the acid. Yep, it gained. Ammonia is a big one. Ammonia is always going to act as a base. NH4 plus is always going to act as an acid. HF is an acid. F minus then is the base. Acid, base, base, acid. Acid, base, base, acid. Acid, base, base, acid. And there's ammonia again, base, acid, and acid, base. All right, so acid-base pairs, that's what they refer to these as. Sometimes a conjugate acid-base pair, referred to that way as well, and sometimes an acid and conjugate base pair. But acid-base pairs is good enough. So we're going to talk about the relative strength of them coming up too, but some more practice. So these are right from your book, example 15.1. and then practice 15.1. I will do the answer to this one. You can do this one, and then you can go look it up at the end of the chapter. These are at the end of the chapters. So first one, again, if you want to try these, hit pause. All right, so acid, and there's the base. So water's acting as a base here, and H3O plus is the acid that you get from water acting as a base. Here, though, it's acting as an acid, and this is the base. And so this is so the base becomes the acid, and the acid becomes the base. Notice OH minus will always be the base. H3O plus is always going to be the acid. I guess I could do these so you don't have to look them up. This is an organic way to do a base. You'll see we don't really know what C5H5N is, but notice over here how they do it. C5H5NH plus. So this is the base, and then it forms that acid. Water's acting as an acid. Base. Base acid. Acid base. Which is not an acid base conjugate. So there's that conjugate, but really just an acid base pair. So does CH3 parentheses 3N become CH3 parentheses 3 NH plus? And the answer is, yep, this one is. How about H2SO4 and H2SO3? No. Remember, dancing hydrogens. Dancing hydrogens, not oxygens. So we have H, and we're lacking an H plus. So this one is, yep, this one's an acid. There's the base. This one would be the base, and that's the acid. But the other one's not. Identify each substance as an acid or a base, and write the chemical equation showing how it's an acid or a base in an aqueous solution according to the Arrhenius definition. So in the Arrhenius definition, remember we're forming H plus ions, or we're forming H3O plus ions. So NaOH, so when you're doing a base like this, you don't actually add it to water. You just say that it is aqueous. So whenever we have a hydroxide base, so there's the definition of an Arrhenius base, where it is giving off hydroxide ions. H2SO4, these I do like to add to water. You don't have to. So if you don't do it to water, you'd have H plus and SO4 minus 2. Or you could have, because what you'll find with these, which is a new thing, they actually lose their hydrogens one at a time. So if we have lost a hydrogen here, H2SO4 becomes HSO4 minus 1. But I like the hydronium ion, as I said. So what I do is every time I have an acid, and with bases, hydroxide base, it doesn't work. But with acids, I always add it to water. And then instead of just breaking it into H plus, then you get that. So now we have an acid base pair. See, in this one, you don't have an acid base pair. You only have the acid becoming H plus for some reason, which again, we could say aqueous. So this is not the Bronsted-Lowry definition, but the Arrhenius definition, which is why we can do it this way. But I still like to do it this way. As you'll see, there is a reason for that coming up. HBr. So same thing, HBr plus H2O. I always add the acids to water. And you always lose one hydrogen at a time. So this is a better one for H2SO4. And then strontium hydroxide, again, a hydroxide base. You don't add it to water. Well, we do the stoichiometry. You could lose 2 hydroxides at a time. That's right from your book. Identify in each reaction the Bronsted-Lowry base, acid, the conjugate acid, and the conjugate base. Like I said, we don't really differentiate. So acid, base, base, acid. Base, acid, acid base, acid base, and base acid. See, water is easy to pick out. This one, then this must be the base, and that would be the acid. Yep, and then this must be the acid, and that is the base. Write the formula for the conjugate of each. So the conjugate is formed after the H plus is lost. So you just make NH3, oh, conjugate acid, sorry, after the H plus is gained. These are all bases. So these are all bases, and we're trying to turn them into an acid. So we are adding an H plus. So NH4 with a +1 charge, the ammonium ion. This one's already -1. So when we add the acid or the hydrogen ion, it becomes neutral. -1 again, add the hydrogen ion and it becomes neutral. Here's that H2SO4 losing 1 hydrogen at a time, like I said. And this one's -2, so we're still going to be -1. Okay, so as for the strength, so this is going to go through this pretty quickly, and we're going to spend a lot more time on this tomorrow. Because in order to do pH, you must understand acid-base strength. And really, in order to truly understand pH, at least in chemistry, you have to understand equilibrium, which is why we don't do it in the first year. Okay, so a strong acid or base 100% ionizes. Remember back to our net ionic equation, that means it's an electrolyte. Putting it another way, it undergoes complete ionization. For example, for the strong acid HA and the strong acid MOH, the following reactions go to completion, completely to the right-hand side. In other words, no equilibrium. And with no equilibrium, that means we are back with this type of reaction to our stoichiometry, where we can do mole ratios. In fact, the molarity of an acid or base is directly related to its stoichiometry. So we're back to arrows and not equilibrium, double-sided arrows. So what is the molarity of each product if you start with 2 molar HA? All right, so here's our reaction. There's 1 hydrogen that's being ionized. So if the molarity of HA, so we could do this as 2 moles of HA per 1 liter of solution. Oops. 1 liter of solution. That's molarity. It's moles per liter. So now we can do the stoichiometry, which is there's 1 HA, and we're looking for each product. Well, it's 1 to 1. So 1 H3O plus or 1 A minus. And so 2 moles per liter or 2 molar H3O plus, and it would also be 2 molar A minus. If this was MOH, you could see it's the same. But if it wasn't MOH, if I had changed it to MOH2, now that makes a difference because now we have 2 hydroxides. So if this is 2 molar, this is 2 molar, but this one would be 4. Stoichiometry. Think of the stoichiometry again. So that's going to have a great impact on what we're doing tomorrow. Now, why is it different? If you have a weak acid or base, if the base is often organic instead of using hydroxide bases, but you will see it sometimes even with hydroxide bases like we just did. So for example, HX, but this time it's weak. We have a K value. We have equilibrium arrows. Why? Well, it doesn't 100% ionize. It's not stoichiometry going from the left hand to the right hand side. Instead, it's directly related to its K value. So now, as I alluded to last unit, it's Ka when you're doing an acid, and it's Kb when you're doing a base. And the greater the Ka or the Kb, the stronger the acid. Things like hydrochloric acid, which we consider strong, has a huge K value, like in the thousands, 10,000s, I think. One of them's in the 10,000s. Whereas weak acids are going to be like times 10 to the minus 5, times 10 to the minus 7, like times 10 to the minus 10. All right, so what is the molarity of each product if you start with 2 molar HA this time? All right, well, now it's trickier. So HX plus H2O is in equilibrium with H3O plus and X minus. Here's why I like always to add water to acids. Now I can do the ice chart because it's equilibrium. Remember, water doesn't matter when we do an ice chart. Water is a pure liquid. It is not included in the equilibrium expression. So I usually cross it right out like that. And I'm starting with 2 molar X. Well, I know it's got to go this way because there's none of this and none of this to start with. And it's always going to be minus X and then 2 minus X. So then over here, we're going to have plus X, and we have X and X at equilibrium. So now I can write the Ka expression. The Ka is equal to the H3O plus, the X minus, over HX, no water. Well, I know that Ka is 2.75 times 10 to the minus 9. X and X is X squared over 2 minus X. So this is a quadratic equation issue. But we learned about this minus X. I can simplify this algebra, and I didn't put any of these on the test. I tried to make the math easy. I basically tried to give you 100 yesterday. Hopefully you got it. But remember what I said about orders of magnitude. This is 0.000000275, and the molarity is 2. So if I were to subtract, you can see it's not worth it. Ignoring this makes so much more sense. So we ignore the minus X. Now that only works if it is not 5% ionized. If it's less than 5% ionized, we're good. So we do have to check that in the end. All right, so let's solve this. So I have, you're not gonna make this. Let me just grab my other calculator. All right, so I have 2.75 times 10 to the minus 9 times 2, and then that equals X squared, so then the square root. So X equals 7.4 times 10 to the minus 5 molar. So X is 2, and we're only producing 0.00000012347 molar. So that's all you get of H3O and H plus when it is a weak acid. If this was a strong acid, it would 100% ionize. So the minus X and X would be 2. So this would be 2 and that would be 2 like we saw before. But the fact that it's weak and it's equilibrium, we have to do what we just had a test on. So hit pause and try the base. And the base. Now we have a KB expression. Well, everything's going to be the same. We have an ice chart. Water doesn't matter. 2 minus X, 2 minus X, 0, 0, plus X, X, and X. I'm going to skip the equilibrium expression. Ignore the minus X. So now we have a KB. Once again, it's times 10 to the minus 7 compared to 2. So once again, we're going to ignore that minus X, and it's going to be a valid reason. I didn't do the valid reason. Oops, I'll do it this time. So X is 1.29 times 10 to the minus 3 molar. So what I said you got to do is, how much is X compared to the initial? In other words, the minus compared to what we're subtracting it from. So what we do then is a percentage. So we put 1.29 times 10 to the minus 3, which is what I got for X, divided by the initial molarity, and then times 100. And this is our percent ionization. So divided by 2 times 100, and you can see it comes out to be 0.06% ionized. So way less than the 5% that we would have to worry about not ignoring this minus X. Now, if you have the ability on your calculator to solve the quadratic equation, you could always do it. It won't be points off. But remember, this test is timed. So, we have to be able to do that on the exam. All right, so one last thing. Don't confuse strong acids and bases with concentrated or dilute. Strong and weak is not the same as concentrated or dilute. So there's the rules again that we learned when we were doing that. And don't be confused by dilute and concentrated. So something that is concentrated but a weak acid means you don't have concentrated is really only going to tell you how much water is there in relationship to the acid. It's still going to ionize the same amount. So it can be a weak acid, meaning it ionizes, less than 5% probably, or right around 5%. You can see the last one was 0.06, but it's concentrated. So if we look at these pictures, and I know you don't have a color-coded version, but you can see the doubles. So we have the hydrogen ion is represented by the circle. Maybe you can't tell the difference. I don't know if you can tell the difference in the shading, but you can tell with mine. So you can see we don't have a lot of water molecules in this one. So this one is very concentrated. Same with this one, concentrated. So there's lots of acid in relationship to the water. This one, lots of acid. This one, there's lots of water in relationship to the acid. So this would be dilute. So with this one, lots of water, dilute. But what does it mean to be strong or weak? Not concentrated or dilute. Strong or weak means strong is 100% ionized. So every acid, so these are the two strong ones, because you can see you don't have a single acid molecule still intact. Every single one is ionized. So these are 100% ionized. Whereas that one's ionized, that one. So you can see this one only has very few ionized. So this is what we mean by a weak acid. So you can see there's an ionized, so that's an ionized. So again, we have a very weak acid in that it's not very ionized. So don't be confused with concentrated versus dilute. All right, so tomorrow's pH.